So let's talk about recurrent neural network. Why do we need recurrent neural network? So here we have the traditional neural networks. Here we have the diagram and the equation. So as usual, we have a single neuron structure. We have the inputs multiplied with the weights and added with the bias. This is passed to the activation function to yield the output. So here you can see this is a one-way street, also called feed-forward neural network because it's in one-way direction. So here we can observe a single flaw. So what's the flaw is after the output is being produced, the whole neuron resets. So this is the single flaw. It goes into total amnesia. So as a result, if we have like sequential data, for example, we have time series, which is stock market or video frames. So this in this type of data, the order cannot be changed or audio. So these are the sequential data. Like if we take example of videos, frame 1 is related to frame 2. So each frames are related. So but if the neuron resets every time, this information is not retained. So in order to retain, it needs more context of all of the frames, or it or in other words, it needs an internal state in order to maintain or retain the information, which is not available in the neural networks. So also the other flaw here is that the standard neural network, the input is fixed size. So if we take example of a sentence as an input, like a sentence can have any number of words like 3 words or 30 words. The input size is variable. So this is not accommodated by the neural networks. So if we take a practical example, let's take an example of this sentence. Bird was good, not bad. So this is a complete sentence. So if we take a look at this sentence and do sentiment analysis by human, you can see like the food was actually good. This not bad is just an indicator that it was actually good. But if we just run a traditional neural network for sentiment analysis, it might encounter this word bad and immediately think that this sentence is negative. But actually, if it retained the information of the previous words or the previous information, like here, this context says that it's actually good. So this is actually positive. So neural networks fail to give sentiment analysis for this one. So that's why we need RNN, which is a self-looping network, which we will see now. So let's talk about the single unit of RNN network. So this solves the amnesia problem which we discussed before by maintaining a hidden state denoted by symbol H, where the information is stored so it can be passed across different neurons. So here we have the current data, which is X at a particular time step t, and we have the previous hidden state denoted by ht minus 1, and the new state denoted is ht. So this is actually a rolled form. This happens many times as the self-looping with the same weights is being done. So the unrolled version, which we can discuss it later with the equation, so we can see how it's maintained. So this is like the compact form. So here we have the input. So here we have the equation, this equation here. This tells us how the RNN updates the memory over time. So here we can see the variables which is being used in the equation. We have xt, which is the input at time step t, which we already discussed, and ht minus 1 is the previous hidden state, which is the compressed summary of the network, which is everything which has been seen before it. And this one is ht, which is the new hidden state which is being generated, which is we're gonna be calculating. And here we have this matrix wxxh, which is input to hidden weight matrix, and we have this one whh, which is hidden to hidden recurrent weight matrix, and we have the bias vector ph. So here we can see the activation function which is being used is Tanh, and let's discuss the operations which is being done in the equation. So first one is input projection. Here we can see there is a multiplication between the matrix, the weight matrix wxh, and the input current input vector xt. So this is a transformation which converts the input representation into the same space as hidden state. So the next second transformation which is being done is the hidden state here. So this matrix determines how the previous memory influences the next memory, which is ht. So next we have the bias. So the bias shifts the activation and increases the model stability. So this part can be represented as the new evidence, as we have the new input and the weight matrix. So we have different weight matrix for this input and the hidden state which is being maintained simultaneously. And this one is the past context, as we receive this from the previous hidden state. So here we are just adding them up. So we are just combining the new evidence and past context to generate the new hidden state. So let's talk about why we use Tanh activation function in RNNs. So here we have the Tanh activation function being used here. So we use this mainly for these reasons. We have zero center output. What does this mean? So Tanh output ranges from -1 to 1, where -1 is the lowest and 1 is the highest, and the center is 0. This is important to represent the influence in the hidden state. What do I mean by that? So it can have positive influence or negative influence in the hidden state. For example, take the example of the sentiment classification of sentence. So here we have a word not. So let's say the food was not good. So here the word not, when it encounters this, the influence of this will be negative because of negative sentiment. Other hand, if it was good, and it will be positive influence on the hidden state. So that's how this tan works. So in other case, if we have a sigmoid which ranges from 0 to 1, we cannot accurately represent this positive and negative influence of hidden state because it's bounded from 0 to 1. So the next reason is the bounded activation. So tan ranges from -1 to 1. So derivative of the tan which is the gradient. So the derivative is the path which the gradient flows. So we need to calculate the derivative, which is this one, 1 minus tan h square z. Here the z is nothing but the computed output before activation function. This is z. So tan h ranges from -1 to 1. Square of tan h ranges from 0 to 1, as square of negative starts from 0 and 1 is 1. So why do we calculate the tan h square? So I missed h here. So h square is because that's what we need and it's in the equation. So from this, the lowest possible value is 0 and highest possible value is 1 for tan square h of z. Using these values and this equation, we can substitute that and we can get the upper and lower bound of this tan derivative of tan hz, which is 0 and 1. So as you can see, its bounded activation means the output here, it's bounded. So the gradient is from 0 to 1. So it doesn't explode. It doesn't go after more than 1 to like infinity. So we will get a stable output. So the problem of exploding gradient is being solved here. So let's take example of other case. So instead of tan h, if we used ReLU, which the upper and lower bounds are infinity and 0. So here the exploding gradients can be occur during backpropagation because the upper bound is infinity. That's why we use tan h here. So neural network operate on vectors and matrices. So the operations like matrix multiplication and addition, they must ensure that the dimensions has been matched properly. So let's see the dimension matching for this equation. So here dx is the input dimension and dh is the hidden state dimension. And here we have the input xt from the equation, which belongs to the real numbers for the real numbers of the input dimension. So input dimension is a real number, which is a vector. Similarly, we have the hidden state vector, and we have the weight matrix, input to hidden weight matrix, which whose dimension is dx multiplied by dh, and we have the dimension of hidden to hidden matrix, which is dh into dh, and we have the bias vector, which also has the dimensions dh. So first let's look at the matrix first transformation, which is being done here, which is the input transformation. So here we have the xt input vector multiplied by the weight matrix of input and hidden. So here this one we have the dimension as dx, and the matrix dimension is dx by dh. So here you can see this vector matrix multiplication, and these two are matching. So this is dimensionally compatible, and the resultant dimension will be dh for this one. Similarly, for the next one, which is the hidden state operation matrix multiplication with the vector. So here ht minus 1 will have the dimension dh, and we have the matrix whh as dh and dh. So these are same. So we'll have the dimension dh. So this is 2. Similarly, for this bias matrix also has the dimension, bias vector also has the dimension dh, so which is 3. So everything has dh. So if we add these two, which we will get the z, which is the intermediate output before activation function. It will also have the dimension dh because they have same dimension, they can be added together. Now let's talk about the output part in this RNN. So it can be calculated at each iteration. So here we have the output state OT from here. So in each state, we can predict the output. So this is the predicted output YT at the particular time step T. So here this can be represented as HT, which is the hidden state vector multiplied by the matrix hidden state, weight matrix hidden state to output Y, where the dimension of the matrix WHY is the dimension of the hidden state and it is state vector by the dimension of the output here dy. So here we get the raw scores. So if we do the softmax, we'll get the probabilities, which is the predicted output. Let's talk about the equations of the unrolled recurrent neural network. Although the compact diagram shows self-loop, the RNN can be unrolled through time. So let's say we have three hidden states, three equations. So here if we have the hidden state 1 and the input 1, the first input, and we have the second hidden state where the output from the first hidden state is given to the second state, and similarly the next state for the third hidden state, and so on. So here we have these inputs x1, x2, and x3. If we observe, the weight matrices remain the same. in all the hidden states and the bias. So these parameters are same, and the sharing of these parameters allow the model to learn a single transition function that works across all time steps. So more generally, at a hidden time state t is effectively a nonlinear function of all the previous inputs. So this can be represented by this equation for a time step t for a hidden state, because each state depends recursively on the previous one, as we see through these equations. So let's talk about the loss function and the gradient flow and the back propagation in recurrent neural networks. So here we have the loss function L. So L can be any loss function like cross entropy loss function at time steps t. So this represents the loss at time steps t. So we calculate this for all time steps denoted by the summation symbol. So as in the neural networks in the gradient flow, we need to find how the loss function changes. So in order to answer that, we need to find the partial derivative of the loss function with respect to the term which directly affects it, which is the hidden state at time step t. So this term, partial derivative of L by THT, tells how H affects the loss. So usually in neural networks, we do this by chain rule, by calculating what term directly affects it and repeatedly expanding it in order to update everything. So before that, we know that the hidden state at time step t can be written as a function of the previous time step h of t minus 1, because that's how it works. So if we saw the equations in the previous part, the repeated unfolding, we saw that each step depends on the previous step. So the gradients flow backward here. So here with this equation, we can represent the partial derivative which we need to calculate as this one, partial derivative of L by h t minus 1. So here, if we expand this with the chain rule, we know what ht is. We will get this one. So ht is this equation which we already seen, which is the tanh function of the weighted sum, which is zt. So let's focus on the second term here. So this, I expand this in the green equation below. So this can be further expanded into its constituent terms, product by chain rule. So here ht directly depends on zt, as we can see here, because ht is tanh function of zt. So using chain rule and this equation, we can expand this. We know what zt and ht is, so we can go ahead and find the equations for these two. Let's see the first term. First term is nothing but we need to partial derivate this with respect to zt. If we do that, the tan h will be 1 by 1 minus h square t. So we can substitute that. And next we have to do zt by ht minus 1. So this zt is nothing but the weighted sum which we have here already. Partial derivative with respect to ht minus 1 is nothing but this coefficient of ht minus 1. So we will have the weight matrix of hidden to hidden. So we can substitute 1 and 2. We can combine that in the green equation. We will get the equation here. So if we notice, we have the transpose in the weight matrix and we have the diagonal. So why do we have the diagonal in the second part? So if you see here, 1 minus ht square of ht hidden state at time step t is nothing but a vector. So if we derivate a vector, the resultant is a Jacobian matrix. So Jacobian matrix has all the partial derivatives in its rows and columns, corresponding partial derivatives in its rows and columns. So here, diagonal matrix means just the diagonal elements are present, rest elements are zero. So why are the rest elements are zero and only the diagonal elements are present? So diagonal elements, before seeing that, let's see the equation for the ht itself. This is the general equation. So let's say for h1, what will the z1 representation be? We will have tan h of z1. Similarly for h2, we will have tan h of z2. For h3, we will have tan h of z3. You can see here, for each of these equations, the input only depends on the corresponding output. The output also depends on corresponding input, like h1 only depends on z1. It doesn't depend directly on z2 or z3. Similarly for each of these. So if this is true, then partial derivative when we calculate in the Jacobian matrix with respect to the other inputs, which is the off diagonal elements, will obviously be zero. That's why we have the diagonal elements here. So that's the intuition behind why we have the diagonal. So let's see the first term, which is the weight matrix. We have the transpose here. So here, why do we have transpose? Because during the forward pass, we compute z equal to wh. But during back propagation, the gradients propagate using vector Jacobian products, which require multiplying the transpose of the weight matrix Wt to correctly distribute the gradients back to the inputs. So this is a vector, so we need to distribute the gradients correctly back to the inputs, so the dimensions will be correct and we get the desired output. So that's the high level intuition of why we have the transpose here. So after doing that, we have the generalized equation for this part. So we calculated this part, we can replace it here. So this is for a particular time step. So for k time step, we have the general equation down below, the white equation. So for case time step, we can substitute this one here, and we have this term here, and we have product symbol here. Why do we have the product symbol, which is capital Pi? Because here this is nothing but a multiplication of the Jacobian products. So we just multiply each and every product here. So as a result, when we apply chain rule through multiple time steps, it multiplies the Jacobian matrices, and this is a compact notation for multiplying many terms. So if we notice carefully, so this term, the range of this one is between 0 and 1. So that's the gradient which we calculate to be bounded to. So as a result, if we multiply repeated terms, let's say this term is 0.8, if we multiply this many times, it will be closer to 0, and we will have the problem of vanishing gradients, which is the main flaw of the recurrent neural network. So in order to solve that, in order to make this better, we have another architecture called LSTM, which we might see in later videos.